Good morning. Let me know if you can hear me.
I can hear you.
Awesome. Awesome. Let's see. I've got some announcements up here this morning just to make sure we're all on the same page. I am going to do a video on section 3.5 and post that tomorrow. So you guys can watch that. 3.5 is a fairly straightforward section, but it does take a little bit of talking through. It's on moving functions around. Essentially, it's on visualizing graphs from the structure of the function. Being able to take a function and shift it left, right, up, down, flip it around. And I want to use some other tools for that just to make it easier to visualize. So I'm going to make that video. I'll post that on Friday. I am going to put a quiz up for Sunday. I'll send an email out about that. I think I'll send it out due Sunday, but you can do it any day you want. I'll send that out probably tomorrow morning as well. Mostly so you guys can practice the interface with the test part, or the way the way the system handles quizzes and tests as opposed to homework. It doesn't look that much different with the way I've got it set up, but it is timed. It does have some features to it that you want to be able to pay attention to. So having a kind of a trial run with it with a good sized quiz on Sunday would be good. Also give you guys just to practice the material. I don't plan to have it be, graded with any harshness. That way it's not going to penalize anybody for kind of practicing. But I do want to get that practice in, and I'll have you guys send in scratch paper for it as well, so we can kind of just get used to how that's going to work before we do it all for the first time on a test. Speaking of that test will be the last point here. That test is still scheduled for Tuesday. It will appear, and we'll talk more about this on Monday, but it will appear in your view on Tuesday, and it will be open on Tuesday. So you have to do it that day. And you do have to make sure that you do your problems on scratch paper, which we'll also talk about on Monday after the quiz, after we have the quiz on Sunday. You've got to send that in after you're done with the test. So we've got that to grade your work, and so we can give you partial credit for things that didn't work, but we'll talk more about that on Monday. The last thing, the hand-in homework wasn't showing you the files that you had to download to do. I fixed that finally. So on the week 2 and beyond hand-in homework, the file should actually be there, which is nice. I think the one that's due Monday has 2 questions. Granted, the first one has 3 parts, so I guess I'd call it 4 questions. So they're not terribly long. They're just some good things to practice, but I did get those fixed. So if they give you any trouble, let me know. I think that's all the general announcement-y stuff. Anything you guys been working on that you want to ask about or look at?
What is that video Friday?
Oh, that's section 3.5. So the material in 3.5 is a little bit different. It's about taking a function. So if we've got some function, it's got some graph, looking at what happens if we take the function and multiply by stuff and add stuff. What's this same function going to look like if we do these translations to it? Well, it's going to, that 1 is going to make it move it over that way 1. The 2 is going to compress it by a half. The 3 is going to stretch it up and down, and the 4 is going to shift it upward. So it would be what, over this way a little bit. It's going to be more compressed. It's going to be stretched and then lifted up. So it's going to, I don't know, look more or less, you know, if this was bigger and had a scale, we'd be counting scales to make it work. But if we know what a function looks like, we can know what modifications of it look like. That way, if we know that the square root of x, for example, looks like, of course, you all know what the square root of x looks like as a graph, right? If we know the square root of x looks roughly like that, and we want to graph, say, the square root of x plus 1 plus 5, actually, let's go times 2. If we learn how to manage these translations, we can look at this and say, oh, okay, it's going to go back 1, it's going to go up 5, and it's going to be stretched higher, so it's going to go steeper. So this graph of this function looks about like this, all by knowing what the base function looks like and what those translations do. So it's not a terribly complicated section. It is nice to have a whole bunch of graphs on it while we do it. So I'm going to use some other tools to record the video offline, so I can use those tools to show you guys how those things move around. And I'll post that on Friday so you guys can watch it for the homework and stuff on 3.5. And when I post it, I'll send out an email about that and the quiz, just so you guys know it's there, and for the folks who aren't here.
Copy that. Thank you.
Sure. Anything else you guys want to ask about or look at before we continue talking about vertices? I did talk yesterday about the discussion boards, and just clarified that you guys do need to post one reply and one post. But I did also tell you guys yesterday that I'll be adjusting the scores that you guys have there, that you see now, to give everybody who did it the full points for it, because we're learning the system. But I do want to leave them as they are for a day or two more, just to make sure those who aren't here and aren't seeing all this will notice it and go, oh, okay, I have to do it this way. So it'll be, I'm not going to count it against you guys, but we'll get it all worked out. Anything else? All right. So yesterday we were talking about, again, parabolas, and we were specifically talking about finding the vertex of a parabola. That vertex is that, we often think of it as the minimum point, but if the quadratic faces downward, then it'll be the maximum point. But that vertex is often an important part of problems, particularly what's called optimization problems, when we're trying to find a maximum result or a minimum result. So if we're trying to minimize costs or maximize power output, finding vertices is usually what we're looking for. You kind of want to put that in your head. If a word problem particularly asks you to find either maximum or minimum, you should immediately associate that with, I'm looking for a vertex. So if we have some function here, let's say this function is, I don't know, x squared, where do I want to go there? Minus, let's go with 5x. Why not? So let's say this quadratic is x squared minus 5x, and we want to find that vertex. We talked yesterday about taking our function and putting it in a particular form. That form we called the vertex form looked like, oops, a times x minus h squared plus k. So if we had this nice perfect square form, that h and k made our vertex. And we looked at a couple examples of that. I did post that of a video on my Open Math, so as I'm going to with most of these. I did start the recording today, so don't worry about that. So if we turn this into our vertex form, we can just pick out that vertex quite nicely. It's not in vertex form here, so looking at this and determining, oh, I know what the vertex is a little bit hard. But if we did build a perfect square in there, we could pick out that vertex. So let's do that. We know how to complete the square. This doesn't have any constants on it right now, so we don't have to worry about anything other than what are we going to add to make this perfect. Now you guys have been playing with that, so ideally you guys are pretty happy with the idea that we take the linear coefficient, the coefficient of the x to the first, divide it by 2 and square it. So the negative 5 halves squared is going to be 25 halves. Now, we can't just add 25 halves to our function. We do have to compensate for it. Usually we'd think of add it to both sides, but I do want to have this side stay a nice clean f of x. So instead of adding it to both sides, I'm going to add it and subtract it to the same side. That way I've functionally added 0 here. Now, of course, we could cancel those back out, but we just put that there on purpose. So don't cancel those back out, because we want to essentially isolate these 3 terms. That was our goal, because they are now factorable as a perfect square, x minus 5 halves. And then this negative 25 halves just becomes our constant. So now that we're in vertex form, we can pick out our vertex. We do have to be a little careful. This h already has a minus on it up here. So this, this x minus 5 halves, our h is 5 halves. It's not negative 5 halves. You might remember we talked about this vertex occurs because it's what makes this factor 0. So the positive 5 halves is what makes this a 0. So if that helps you remember to make sure that sign changes, then great. And the y value, though, of our vertex, negative 25 halves. So that's that point.
Wait, why did it change?
2 reasons. One, the main one is because it has to be the number that makes this 0. Yeah. And it's really the same thing as when you have like x plus 5 times x minus 1 equals 0. And we say, oh, our answers are negative 5 and positive 1. It's because we're setting each of those equal to 0 and saying, okay, what makes this a 0? Negative 5. What makes this a 0? Positive 1. So it's the same reason as we did that. It's just in a slightly different position or for a slightly different argument.
Right.
So that's the kind of the nice version of finding vertex. So, we had to deal with the 5 halves, but we didn't have any kind of nasty coefficient out here or anything. So, this was a fairly nice version. We did look at a little bit uglier of one yesterday. And I think it might be in our interests to look at least one more that's a little bit on the ugly side. So say we have one.
Excuse me, Matt.
Yeah.
For the one above, why isn't it negative 25 fourths?
I have no idea. Thank you, Crystal. Negative 25 fourths. I got distracted. Now that doesn't change the 5 halves, but it absolutely does change this negative to negative 25 fourths. I'll have to give myself a -1 for that. So if we have a function that's has a little bit more going on in it, let's say 3x squared minus, let's just make it ugly for the fun of it, 7x plus 4. And we want to find the vertex for G. We're essentially going to do the same process. Do the completing the square process here. We do want to remember we have to factor that 3 out. So I'm going to give you a minute or two to try to remember how to do that or practice doing that. It is common to get a question on your homeworks and quizzes and tests that says, okay, given this function, it's usually not this ugly, but given this function, put it in our HK form, put it in this vertex form. So even if you're able to find the vertex other ways, like say you could use the calculator and zoom in on this point and get that point, you still have to be able to put the equation in that form. So we do need to practice that. But again, usually it won't quite be with that bad of numbers. But I'll give you a moment to practice that and we'll look at it. You guys over in the chat, why isn't it 25 fourths? I don't know. It's 25 fourths. So I'm going to try to follow along behind you a little bit here. I'll factor out that 3. It is unfortunate that this 7/3 has to end up being 7/3, but we've got to get the 3 out of the way. So that's the price we pay for it.
Why do you factor the 3 out of just those 2 terms and not all 3 terms?
A good question, because our goal is to turn this piece here into our perfect square. So we're really only trying to complete the square on these parts. We expect a constant to be outside of that, right? So we could factor it out of the 3/4. We'd have to distribute it back to the constants at the end later. So, and it's in some ways kind of a different look at factoring. You usually, when you've factored, you've only factored out something that evenly divides into everything, and you've always factored it out of everything. And usually because you were trying to solve when something's equal to 0, or you were just told factor we weren't factoring for the same for a purpose like this. So it often feels a bit different. Like, you know, 'cause I only want the 3 out of these because that's where I'm trying to complete the square. So I'm only going to factor it out of those. But if you haven't had a reason to do that before, it can look like a very strange thing to do. And that's one of the things that I'll keep mentioning. One of the things about that we do a lot in this course is kind of take things that you know how to do. You guys know how to factor, but we'll use it in ways you haven't before, and use it in ways that are kind of like, oh, I didn't think we're allowed to do that. Fair?
Yes, thank you.
Sure. So that's negative 7/6. And see, that's why I got that wrong. I didn't write it. So 49/36. When in doubt, write it out, right? So that's what we have to add. There is a complication that comes up, Justin, so we do have to be careful right here. So we're adding that 49/36, and really I want that 49/36 and this x squared minus 7/3 x to be isolated, because this is what we're trying to factor. So when we subtract the 49/36, I really want that to be outside those parentheses so it can add to the 4. But here's the dangerous part. Because we added the 49/36 in these parentheses, we've actually added 49/36 times 3. We have built in this product. So when we subtract it, we have to subtract the same product. And gosh, you can imagine that's easy to forget to do. You can, if you want to, avoid that a bit by factoring the 3 out of everything, then doing this adding and subtracting. But then you have to redistribute this 3 to only your constant term, and that's really just as awkward. So either way, there's an awkwardness in the fact that we want this contained in that product, and the compensation for adding the 49/36 has to be handled outside. So one way or another, there's an awkwardness there. But once we've done that, again, we've completed this square, so we know how it factors. X minus 7/6 squared minus that 3 will cancel into the 36ths. So we'll get 49/12 plus 48/12, because 48/12 is that 4 with common denominators.
I'm so confused.
Where happened? Where happened? That doesn't make any sense. Where did that, at what point did you get lost?
I just don't. The whole like factoring only one section and then randomly like this whole process is just confusing me.
Well, let's look at what the other option would be and see if that helps. So let's say you did factor it out of the whole thing, because you certainly can. You'd have 3 times x squared minus 7/3 x plus 4/3. Then we'd be asking the same question, what do we add in there to make it a perfect square? So it would be the same 49/36. So we'd have x squared minus 7/3 x plus 49/36 minus 49/36. Allows us to compensate for the fact that we added that, plus the 4/3. Now this part here is a perfect square. So it factors as a perfect square. So we'd have 3 times that perfect square factored. Notice I do need the double parentheses here. X minus the 7/6 squared minus the 49, 36 plus 4/3. Now, hopefully it makes sense why I need the double parentheses there, because this thing here we have factored, but that 3 is still being multiplied by all of this. And that's what I'm avoiding by just factoring the 3 out of those 2 terms that I want. So, okay, keep going here. That 4/3, we can get common denominators there. So that's minus 49 36 this time. Plus, we'd have to multiply top and bottom of this by 12. So we'd have the 48 36. So that would turn into, oh, just negative 136. That's kind of cool. Times the x minus 7/6 squared. And all of that would still be times 3.
That makes way more sense to me.
And that's fine. If you like this pattern better, then go for it. We do have to remember at the end, though, that this 3, we kind of need to distribute it to both of those and get the 3 times x minus 7/6 squared minus 3 times 1/36, which is 1/12. So really, either pattern is fine. That's what I was saying to Justin. There's a little bit of awkwardness with the fact that we're separating this from the constants. So there's a little bit of awkwardness in that in this pattern. There's a little bit of awkwardness for that over here. Whichever way you want to handle that is fine. Just make sure that, because often what I see people do when they try to do that is they lose these parentheses here, and this never gets multiplied by that 3. So as long as you're careful with that, Andrew, either way works just fine. Cool?
Yeah, just the flow of that other way makes more sense in my head than what you were doing over there. Like that whole pattern makes way more sense to me.
Does it make this also seem more like reasonable? Okay, now you see where those are coming from?
Yeah, I get it, but it's the whole like factoring a section that I just can't. It's gonna screw. I know that doing it that way is gonna screw me up because I'm gonna forget to add that 3 back. Whereas this way, if I do it this way, I can remember that my 3 is always on the outside of my double parentheses.
Right, because you've got that notation to remind you that 3 has to go. Yeah. That, as I said, either way is really, really fine. But yeah, there is that little awkwardness either way. But, and again, this is, without putting in decimals or fractions, this is all of the nastiness we could have happen. So, but once we have it in that form, and we want to find our vertex, again, our vertex is now sitting there for us. Negative 7/6. Oops. Not negative 7/6. Oops. Positive 7/6 and negative 1/12. So if we wanted to graph this and we wanted to place that vertex, well, 7/6. I'm going to say 7/6 is there. And negative 1/12. Shouldn't have labeled it down there. So negative 7/6 is there. Negative 1/12. I'm going to label there. And that's going to be the vertex of our parabola. So if somebody asked, when is this process, whatever this is modeling, when is it at a minimum? It's at a minimum at 7/6. What is its minimum value? Its minimum value is negative 1/12. And you'll often hear that question asked that way. If somebody asked where or when is this becoming a minimum, the input value, the 7/6 is where it's happening. That's when it's happening. What is the minimum? What is the function value? So the what is the minimum is that negative 1/12. That's a common set of emails to get when we do optimization questions. Some of the questions will want the X value, some of the questions will want the Y value, and people often get frustrated. Why is it the X in this one and the Y in that one? It's that subtle distinction in the language, whether they're asking where, what, or where or what, when or what.
I mean, it makes sense if you think about every graph you've ever seen that shows data. It's like when usually goes along the bottom and what is up.
Yeah, it does. It does make sense when you think more about it, but oftentimes if you're working on a problem, it can easily get muddled. A nice example that I like to give is if you're working at a company and your boss comes in and says, what was the most money we lost? And you answer November. That's not what you were asked. You were asked what the value of the loss was, not when it happened. If somebody comes in and says, when did we lose the most money? And you say $10,000. That is clearly the wrong thing. But when it's more abstract and it just says what or where and it's an abstract function, it's often not as obvious. So do be careful, a little bit careful about that language. If you are asked just for the vertex, what is the vertex? The vertex should always be an ordered pair, because a vertex is a point in space. Questions about any of that before we make this easier? You're like, no, make it easier. That sounds great. Not really easier, but just like we did with quadratic formula, because this process is the same no matter what the numbers are. I mean, we didn't do anything different because this was a 7 than we would have if it was a 9 or an 11 or anything else. I mean, it would have cleaned up a little better if it was a 9, but our process would have been the same. Because of that, just like quadratic formula, we can take this tool and abstract it and kind of go, okay, what would we do to every quadratic we could be given, and see if we can find a nice formula. So if we followed the process in general, I am going to divide or factor that a out of just those first terms, but again, you could do it either way. And we try to figure out, okay, what are we going to have to add here to make this perfect? Well, we take that b over a, we divide it by 2, and we'd square it. That's going to give us our a, x squared plus b over ax plus b over 2a squared. We could write b squared over 4a squared, but we're just going to factor it in a minute anyway. And we do have to remember to, oops, not add it. We have to remember to subtract it, the b squared minus 4a squared. We do have to remember to multiply it by the a. We do have to remember to add the c. But frankly, in a minute, we're going to stop caring about all of this stuff over here. I'll show you why. So this now factors into a nice x plus b over 2a squared, just like it always has. The thing we squared ends up being our constant here. Minus, we could do a whole bunch to combine this and get common denominators and stuff, but I don't want to. I'm just going to call it stuff, because it's extra work that we won't use. The important part was right here. This means that the x value of our vertex will always be, well, what makes this 0 will always be negative b over 2a. Yeah, we could use, all this and simplify it to make a formula for the y value, but we're not going to. I'll show you why in a minute. Because this is so little and nice and straightforward that I don't want to add a big nasty formula to it. So nice and straightforward that, it's a tool that's hard not to use. So automatically we could jump up if somebody gave us y equals, 4x squared minus 5x plus 1 and asked us to find this thing's vertex. Instead of doing all of this process, we can find the x value of the vertex just by taking that negative b over 2a. The b is negative 5, so the opposite of the negative 5, over 2 times the a value of 4, and we get a nice 5/8. So the x value of our vertex, 5/8. Great, that was nice and fast. The problem is we need the y value as well. And again, we could have this big formula for the y value, but we'd have to memorize that, and it's ugly. And we don't need it because we already have a tool for finding the y values given an x value. That's what the function's supposed to do. If you want this y value, plug in the corresponding x. We know the x value. It's 5/8. So if we take that 5/8 and plug it back into the function, evaluate the function, I'm going to write in function notation here, evaluate the function at that 5/8, light blue is probably a little hard to see, sorry. If we evaluate the function at that 5/8, we'll get the y value for the vertex. Now you might not like putting 5/8 in there, but trust me, it's better than having to memorize what this simplifies down into. It's not that hard to memorize it, but nice to have to memorize less. So all we have to do is evaluate that. Should take a moment and evaluate that function at 5/8.
I have a question.
Shoot, what's that?
So this whole function, right, at least like the math part right here, can just be plugged into a calculator. So if I did that on like an assignment, would I get knocked down for not showing my work?
It kind of depends. The short answer is yes, we need to be able to do this by hand, partially because at times the 4, the 5, the 1, those will sometimes not be numbers. There'll be other functions. There'll be A's and B's. There'll be variables, and we'll need to be able to answer these questions in terms of those other variables. And the calculator can't do that.
Okay, but like in this one where it's just numbers, I could just plug it in.
You could, however, let's say this 4, instead of being a 4, was a 7. 7s don't have, we'd have, 5/14. 5/14 is fine, but the decimal for 5/14 is infinitely repeating.
Yeah, you can, at least on my calculator, I can just plug that in and hit the fraction button, and it gives me a nice answer in fraction form.
Right? But when you plug it back in here, often, sometimes, not always, sometimes the approximation of that approximation can sometimes yield things that don't turn back into the proper fraction. Does that make sense?
Sort of.
Also, if we wanted to be, kind of just almost mean about it, you put a square root on that, and the calculator's never going to give you a correct value. It'll give you a close approximation, but never a correct value.
I hate fractions.
That's common, but we've got to get past that. We've got to push through that. We've got to become strong with them. I gave that, I don't know if you hear the other day, I gave that example I always like, people who hate fractions, I'd like you to multiply those together. Okay, yeah, you can ask your calculator, and it doesn't take, if your calculator's out there and in front of you, you can certainly do it. But once you know how to multiply fractions, this is just so much easier to do.
Oh, it's not that I don't know how to multiply fractions. I just hate finding the least common denominator and all other annoying shit.
The more you do it, the faster and better you get at it. And I definitely will never argue with something that never argue with anybody that it takes a while to get there. But the more that you try to find ways to avoid doing it, the longer you're going to spend fighting against it. And, the fractions aren't going away, and eventually they'll win. Particularly for those of you who are going to go on to Math 112 or calculus. You'll be dealing with more and more numbers that are irrational, more and more abstract objects, more and more fractions with functions in them. So you'll need those tools. So better to try to strengthen them now than hit that wall later. And I know that's always a little bit of a, I guess, harsh answer, do it anyway. But it is true, unfortunately. People often ask that question about, can I do this without having to do the fractions? And yeah, there are often ways to do it. But as the person who's teaching the math class and who teaches a lot of Math 112 and teaches a lot of calculus and so forth, that question always translates a bit in our ears to, is there a way I can avoid learning and growing in the area I need to? And I know that's not really what you're asking, but you got to push that as much as you can. Andrew, is that fair? Maybe not.
Yeah, I mean, I get what you're saying, but like this whole situation right here, where you have 4 times 25 over 64.
Mm-hmm.
Now you have 25 16ths. Like, I'm so confused.
Well, we got 4 over 1, right? So that 4 divides into both of them, leaving a 1 there. 4 divided by 64 is 16.
So we just multiplied them. Like, yeah. That's what confuses me. So how is that multiplying? Wouldn't it be like 100 over whatever 64?
Sure. And if we had 100 over 64, you would at some point go, okay, there's a common factor in those, and say that's 4 times 25 over 4 times 16, and then reduce those 4s. Often when we multiply, if we're going to cancel it out later, why don't we cancel it out beforehand? So essentially what we're doing is looking at it as 4 times 25 all over 1 times 64, and canceling that 4 out before ever even doing this multiplication.
Okay, so then when you're dividing fractions, are you just doing like the opposite of that? You're just like multiplying. So like it was like 7/3 over divided by 2. So what are you just like cross multiplying or what?
Well, what we can think about it as is this dividing by 2 is the same as multiplying by 1/2, multiplying by its reciprocal.
And then you're just multiplying straight across. I got it.
But if this was, say, like a 10 up here instead, say,
yeah,
instead of getting the 10/6 and having to reduce that, I would divide this 2 out first to make it easier.
Gotcha. I hate fractions.
But hopefully you can see a bit the more experience you get with them, the more you can avoid the bad parts, and you can do things to get them out of your way and reduce them before having to have them be, big, ugly numbers that you then have to reduce. It takes a while to get there, but
Well, it makes sense because if you're multiplying two fractions, you basically have like, whatever times whatever over whatever times whatever, and you can cancel those things out because you have one giant division problem essentially.
right. But to do that, you've got to get comfortable with the idea of cross canceling, and which is one of the things that's called. But oftentimes when people are working with fractions, particularly who don't like fractions, is they'll go things like, you don't have to cross cancel, so I don't want to put another skill into my fractions. I just kind of want to do it this way because that is how I first learned, and that's what made sense. But often what that does, unfortunately, is it limits the tools that make dealing with fractions easier, so they stay hard, if that makes sense. So I don't want to lose sight of our nice question down here. We did get common denominators in here because we need the 16ths. I do want you to notice something. Notice this is 25 16ths and this is 50 16ths. So this middle term here is twice the size of that term. That always happens when you're finding a vertex because of the symmetry involved. The term that you get for the x term will always be twice what the x squared term is at your vertex. So I almost use that as a check. If I'm trying to find a vertex, this step where, hey, wait, that's twice that, that's neat, is always going to happen. So I kind of look for that as okay, good, this is going the right way. Need common denominators here. And common denominators are one of those things, they never go away, unfortunately. So what is that? -9 16ths? So our vertex, 5/8 and -9 16ths. Before I let you go today, unless there are any burning questions about that. Before I let you go today, I want to go through a quick and smaller scale example of what we need to be able to do with our quadratics. So let's say we're given a substantially nicer quadratic. So let's say f of x equals, well, let's go super nice here. How about x squared minus 3x minus 10? 10? Yeah, 10. We should be able to, given any quadratic, we should be able to find its y-intercept. We should be able to find its x-intercepts, if it has any. Not all quadratics do. We should be able to find its vertex. So these are our kind of three primary things we want to be able to find. Oftentimes, because for our application problems, say, this one's going to face up, but say we had a quadratic that was opening downward, we'll often want to know, where was its maximum height? Like if this is a projectile, where's its maximum height? Where did it hit the ground? Where was it launched from? If it was launched from a height above the axis. So being able to distinguish all those pieces essentially comes down to being able to find y-intercepts, x-intercepts, and vertices. So just real quick, how do we find each of these things? Well, if you want a y-intercept, the one thing you know about every y-intercept is that its x value is 0. So wherever this thing's y-intercept is, we know its x value has to be 0. So if ever you want a y-intercept, plug in x equals 0. For polynomials in standard form, it's very nice because 0 squared is 0. Negative 3 times 0 is 0. So you're just left with that nice negative 10. So we have a y-intercept at 0, negative 10. If we want x-intercepts, similarly, the one thing we know about every x-intercept is that its y value is equal to 0. X-intercepts are on the x-axis, so they have a y value of 0. So if you want to find an x-intercept for anything, let the y, or the function, equals 0. We've talked about a couple different ways of solving quadratics. We could try to complete a square here. We could put it in the quadratic formula, but don't forget your factoring skills. If your factoring skills are not strong, strengthen your factoring skills. They will be necessary and important. So x equals 5 and x equals negative 2. If you can factor something, you're usually more accurate, faster, cleaner, happier. So our x-intercepts are going to be at 5, 0 and negative 2, 0. So negative 2, 0 and 5, 0. To find our vertex, we could put this in vertex form if we wanted to by doing the formal completing the square, or we could find the x value of the vertex with that negative b over 2a. So the x value in this case, if we did that, would be 3 over 2 times 1, so 3 halves. And then we can plug that 3 halves back into here. So 3 halves squared minus 3 times 3 halves minus 10, 9 fourths minus 9 halves minus 10. So 9 fourths minus 18 fourths. Again, getting common denominators. Might as well turn this into 40 fourths while we're at it, since we're going to probably want common denominators for that too. So negative 9 fourths minus 40 fourths is negative 49 fourths. So our vertex, that's the y value of our vertex. So 3 halves and negative 49 fourths. So that would be about here. 3 halves, negative 49 fourths. And we have all the pieces of our quadratic. It is often nice, by the way, this point here at 0, negative 10 would reflect to here. We know the axis of symmetry, it's called, is here through the vertex. So we're symmetric around the point x equals 3 halves. So if it takes 3 halves to get to here, it would take another 3 halves to get to there. So half of 3 plus another half of 3. That point is just going to be at a nice 3, negative 10. So people often like having that point symmetric to the y-intercept. So that's often just referred to as the symmetric point, but it is specifically symmetric to the y-intercept, just because it gives us a nice 5-number plot. or 5-point plot of a quadratic. So you'll get some questions like this on, homeworks, quizzes, and tests, and it just kind of brings together all of the tools. It allows us to practice our solving. If we have to use the, completing the square or quadratic formula over here, we can. It allows us to practice finding a vertex, and it reminds us about y-intercepts. So, practice. Questions about any of that? Hopefully you can see we're taking the kind of skills you've been exposed to and trying to push them to a new level, working with them with the fractions we might not be comfortable with, working them with, some slightly modified techniques, putting a lot of different tools together. That is a lot of what this course is about, taking the skills that you guys have developed and making them more robust, rounder, more flexible, so they can be used in the ways you're going to need them for the classes to come. Your programming classes, your science courses, your other math courses, your sociology courses, your business courses, all of those things that want this class. They want you to be able to manipulate things in this kind of more flexible way. So a lot of what we're going to be doing is stuff like this, taking things and rounding them out. All right, anything else I can do for you guys today before I let you go?
Is this test going to be more like a take-home test or like an in-class test?
In many ways, it'll be a lot more like the homework, except you only get one shot and it's timed. That's the short answer.
So like in a regular test where we could go back and maybe change our answer, this one we can't?
You can, essentially, like the homework, you can put in answers and then go to another question and work that question, go to another question and work that question. Your answers aren't locked until you hit submit.
Okay.
So I often recommend kind of go through the test, go back and forth, play with them, and then when you're ready, when you're done, go submit. And again, if something goes like terribly awry on the homework, it's easy to like miss a decimal place or move a negative or something like that, and get it totally wrong. And we'll talk about this more on Monday. But having that, scratch work with you, that's really nice and organized and well written out scratch work that you will then upload to me. I'm going to go through those. It'll be fun to see how long it takes. Go through all of those and go, oh, okay, this is why they got that wrong. I can give them some points back for partial credit on that question, some points back for partial credit on that question. So you will have that opportunity. So it will be better than just if you were just doing it as like homework with one shot. That would be a lot. I would be a lot more nervous if you didn't have the opportunity for that scratch work. Okay. Anything else?
Nope.
So with the hand-in homework for week 1, was there a question that was involved with that, or?
No, I just wanted you guys to get the practice of uploading anything.
Okay.
You could have uploaded a picture of a bunny rabbit, and I'd have been fine with that.
That's what I thought, but then when I looked at it,
I haven't scored them yet. Yeah.
Oh, okay. I was just like, when I looked at what it read, it kind of reads the same thing every week. So it was saying about downloading a file, and I was like, kind of like, well, I don't see a file to download.
Yeah. Well, that's when we started. I said I fixed that. So when you see week 2 and so forth, you should see those.
Totally. I did hear you say that, but I was just trying to make sure that I did the first one correctly. Which
You're good.
So back to that hand-in homework on week 3. I accidentally used a late pass because I thought I didn't do it because it showed like it showed no points. And I was like, I thought I turned something in. And then I clicked a late pass. So I was like, oh man, I got to turn this in. And then I had an upload there. And I was like, oh crap, I just wasted a late pass.
Send me a message on my Open Math and remind me, and I can I can hand it back to you.
That would be awesome.
Yeah,
Because
that's easy.
I thought maybe I didn't do it, and I was like, oh no, wait, and then I actually did it, and I was like, oh shit.
No problem.
Oh,
Thank you so much.
You're welcome, Justin. Aaron, James, and Ava, haven't heard much from you guys today. You guys doing good?
Yeah, I'm doing good.
Okay. If there is anything you guys come up with that you need, just let me know.